Welcome to my talk, Tales from the VRP, V8 VRP, a Post-Mortem. Why it's a Post-Mortem, we'll see shortly. First, okay, no, wrong window focus, sorry. So, no. Okay. Yeah. Okay, this, you might know me, might not know me under my real name, but you might know me under my online handle, Popax21. I'm an independent, that's, okay. But yeah, I'm an independent security researcher focusing on low-level applications, and most of my work has been on V8, aside from CTFs, where I play with like some local Austrian teams, but I also participate in ECSC and ICC for Team Europe. You might have known my CVEs. I have a few V8 bugs and some CVEs from them, and today we'll take a deep look into one of these bugs. But first of all, first of all, what even is V8? Why is it like a target that's worth looking at? That's just for the people who are unaware. Basically, V8 is the JavaScript engine of Chrome or Chromium, and as said, that probably means it's the most vulnerable attack surface of any major project these days. If you know, most people you know will probably use Chrome, and if they visit some sketchy website, V8 will be the first attack surface available to them. Aside from Chrome, it's also used in Node.js, which popularized it on the server side, but that's a bit out of scope because if you can run JavaScript in Node.js, you already have compromised the system. Aside from Node.js, it's also used in Cloudflare workers and a bunch of other serverless app stacks. Cloudflare is just the only one to admit that they're using V8, so the V8 security boundary is not just defending you from malicious websites, it's also preventing cross-tenant attacks in like very popular serverless products. So it's like a very valuable target, so definitely worth your time. If that's not enough to motivate you, you might want to look at the dark side, so the rewards tables. We only care about the last row, and basically, if you know what you're doing, you can make this your full-time job. At least you could before AI. Now you get like, yeah. Yeah. Well, I'll have some thoughts on this change later in the talk, but for now, we'll have to move on. Let's just say this was a viable full-time career. Now it's not, so we have a post-mortem here. But I think we have enough AI talks at this conference, so I'll focus mostly on the actual technical aspects for now. Basically, I will just give you a quick journey through like how one could find a V8 bug. Like what is the typical autonomy of a V8 bug? What do you need to look out for? What are lessons we can like generalize outside of V8 if you still look at it or to other targets? So this story starts, like all good stories start, at a 8-hour airport layover in late 2024. And me, not knowing what else to do with my time, decides I'm just gonna open source.chromium.org. Well, what else am I gonna do? I'm not gonna be productive in some other way on an airport layover because I'm probably sleep deprived. So, yeah. My target this time around was a focus function deep down in this file called unwind and find handler. Its name is what it does. It's responsible for unwinding the stack when you throw an exception in JavaScript. So like if you have a throw new error somewhere, it's responsible for going through the stack and finding which try-catch block should handle it and doing all the other stuff. It's an interesting code path for reasons we'll elaborate later, but for now we'll just say this is what we're looking at. The code is slightly long and slightly complex. It goes all across the V8 codebase, touching many, many different aspects. It's like a central linkage point, so not really easy to understand at a first glance. So I do what any people would do in this situation. I just start looking at it, just reading it line by line. We have this structure here where we have a for loop, which has a stack frame iterator, which I assume iterates stack frames. We then have some logic for stack frames, and there's some logic here for stack switching. What's stack switching doing in V8? So this starts a rabbit hole where I start tracing the cross-references of this and just, spending a good 3 hours just figuring out what the heck is going on there. And yeah, now I'm going to spare you all the messy details and just give you the overview of what this is about. So we have a very simple program here. We have like an outer function that wraps an inner function, and the inner function does something. If we trace the execution of this, we'll see at first see the entry frame, which is just V8 starting up. And then we'll have an interpreted frame. V8 is can optimize, but for now we have no optimized code, so it's us just interpreting. We see it's running the top level code, then it goes into the outer frame, outer function, then it goes into the inner function, it logs something, and then it returns. Very, very simple. Not really so many surprises there. Now, what happens if we make these functions async? Async, I hope everyone is aware of what async does. Async basically just means that the function doesn't run synchronously. It can yield execution at any time and then return. How does V8 implement this behind the scenes? Because the stack frame here is not a logical stack frame, it's like the hardware machine stack frame. And like the machine doesn't really have a concept of yielding execution and not on going back, except for like threads. But does V8 like spawn a new thread for every async routine? That would be slightly inefficient. So let's see what it does instead. We have our entry frame, we have our top level frame, then we go into outer, still an interpreted frame, but now we diverge. The first thing the outer frame does is it calls async function enter, which is a V8 built-in. What it does is relatively simple. It sets up a promise object, which is like a JavaScript object that encapsulates some work being pending and allows you to like run code once the work completes or stuff. The JavaScript and web developers here will hopefully know what I'm talking about. And once it's done, we just continue execution as normal. We go into outer. Outer does the same async function enter dance, and then we enter fetch, which goes through some translation layers and ends up in C++. This will also set up a promise object and everything, and then it will return. But we can see, suddenly we're popping all the way back to the outer level frame. We're not like suspending anything, we're just going all the way back down. Well, this outer frame, this top level frame, outer will return a promise object, as mentioned, but it just doesn't do anything with it, so we just return completely. And now we're gone. Okay. But like we still haven't run a console.log statement, so what's going on there? Basically, the name of this function here should have already tipped you off. We have stopped running JavaScript code. We're now running microtasks. Some advanced web developers here might know what the microtask queue is, but very simply speaking, it's like a queue of work items that need to be done. And these work items are run whenever there's no JavaScript code. Like the work queue is only drained when all JavaScript has completely returned execution. And in this case, fetch will have returned, its promise will have resolved, so we have a queued work item for promise fulfill reaction job. Basically, that's what the name says, a promise was fulfilled, and we're reacting to that promise being fulfilled. Then we have a resume generator trampoline, which, we are back in our interpreted frame. The interpreted frame, this trampoline basically sets up the stack frame again, sets up everything as it was, and then jumps back into the function. So we now run a console.log normally, we return, and the inner promise now resolves. So we go through the same dance again, no microtask queue entry, new generator trampoline, we run outer now. Great. Makes sense, but there's still no stack switching there. Well, for that we need to look first at this animation I forgot about. Basically, the important thing is to notice is that we're not running code like synchronously, like our hardware stack being our native stack. We basically have replaced this physical stack with a link from the promise object. So like this is our call stack now, the promise links. So yeah, there's like one issue with this though, WebAssembly. WebAssembly is very low level. It has no concept of async or microtask queue of anything. It runs code and it returns immediately. It can't suspend. So if we have some simple WASM function, we can do what we did before. We call our export. We have some transition logic. Then we go into the WASM frame. The WASM frame calls the inner frame again through some transition logic. Inner does its work, and we return completely normally. Works fine. OK, what if we do make things async now? we run into the same issue. How do we handle this? WASM can't be asynchronous, it can't await, so how do we await inner, and how do we await the outer function? There's no way to do this, seemingly. So what if we just run this code as is right now? If we go in, we see we have set up WASM, we call WASM frame, we go into the inner function. The inner function does its usual dance with setting up this promise, goes through API called exit frame, and we return to the WASM frame. The outer inner function has returned a promise object, but WASM doesn't know what to do with it, so it just drops it. So WASM just continues execution, logs done, even though no work has been done yet, returns normally, and now we're back at nothing. The microtask queue drains because of fetch completed. We continue running inner. Inner completes its work, dispatches a resolution job, but there's nothing to resume because WASM hasn't registered anything. So we're just dead. But yeah, that was a problem in the JavaScript and WASM scene for a long time. There have been some workarounds, basically having the WASM compiler, like from whatever language you're compiling it down from, just create the state machine all by itself, and then just do this dispatch all the way down, dispatch all the way in dance manually, which is like, it works technically, but it's very complex and fragile, and no one really wanted to do this. So at some point, the WASM committee and V8 decided, OK, we're just going to add first-class support for this. The result is JSPI, or JavaScript promise integration. It does what it says. It integrates JavaScript promises into WASM. And so instead of having this typical WASM function stack, we do something else. And this is where stack switching comes in, because as said, WASM has no concept of like as resuming or awaiting, and JSPI doesn't add it. What it instead does is give you the ability to run WASM code on a separate stack. So if you call a WASM function now, it does a bit of a dance, links up stack switch frames, and then it calls your WASM frame on a different stack. OK. Now, if you run a JavaScript function, it has to switch back to the main thread, because JavaScript can only run on the main stack. It does its work. And if it's synchronous, we just return normal, nothing is wrong. But now, if you call an async function from this JSPI setup, we'll have our async enter dance. We return to the WASM2JS frame. But the WASM2JS frame says, OK, I have called an async function. The function hasn't completed yet. I can't return to WASM yet. So instead, it just switches back to the main stack. And this whole dance has set up a promise object for the WASM object. So there's currently, JavaScript now has a promise object, which encapsulates this unit of WASM work running on the right. It's currently suspended because no work to be done, but it's there. So we go back to the mic. We have just return. Then the microtask queue drains because promise fulfilled, which runs WASM resume. WASM resume just reestablishes the link and resumes the WASM work. WASM can then finish, and once WASM finishes, it will call fulfill promise, and this goes through the same dance where it now dispatches resume jobs for like the top level frame and everything that resides on it. The end result is basically that with JSPI, you can just call WASM in async JavaScript functions from WASM. WASM still doesn't know what an async is, but WASM just sees it calling an async function and the async function returning synchronously, even though it's running asynchronously. OK, that rabbit hole complete. Let's just go back to our original function again. We have now finished understanding this small fraction of code, just on a conceptual level. If we dig into the details, we'll be here for another few hours, so just let's say this is good enough and move on. And let's go to the next block down. There's a bunch of logic we could all dig into. It's like a huge code base. As said, this is like a really bad example of like everything just being meshed together into one giant melting pot. The next step that we want to look at is this. Code can de-optimize, code marked for de-optimization. Something about lazy de-optimization and having to jump to the original return address. It's messing with return addresses? Huh. Let's see what that's about. And as suspected, another rabbit hole starts. We'll do the same dance again of just explaining what this is all about, and I'm sparing you the technical details. For this, we'll just have a simple add function. We have already like seen some execution traces, but now we'll go into a bit more depth of one. Basically, we have already been running interpreted frames now, but V8 is known for executing JavaScript fast, which is like quite a feat. So how does it do that? What happens if we just call our add function, which as now just executes null with interpreted frames? What just happens if we just run it a bunch of times? Oh, something happened. And if we can see, not sure if like the contrast is good enough. OK, the contrast is really bad, sorry. But basically, first of all, we have switched from interpreted frames to turbofan frames. Turbofan is one of V8's JIT. Yes, V8 has several JIT compilers. But for now, we have like reached the maximum level of optimization that V8 can provide. And but there's something else that has gone on. Add has gained a new line of code. Not sure if you can read it, but it basically says if A is not an SMI or B is not an SMI, deoptimize. SMI basically just means it's an integer. So basically what V8 is saying is if A or B is not an integer, then call whatever deoptimizes. But in exchange, it seems to have been able to optimize A plus B for integers. And because this is JavaScript, someone could just pass an object in here. But V8 has made the assumption add is always called with integers, so I'm going to optimize it for being called with integers. What happens if we break that promise? We just execute, turbofan frame runs, we have run into this check, we don't have an SMI, and a turbofan frame turned into an interpreted frame. And it's not like I called a check that happened on the caller side, it happened in the function itself. So yeah, that's basically what eager deoptimization is. V8 sees your code. Because it's JavaScript, it could take any sort of argument and any sort of assumption. And like everything, if you have to act defensively every time, you can't really optimize it. So V8 instead observed that, hey, add was only called with integers. I'm going to assume that it will only be called with integers in the future. So I'm going to optimize with this assumption in mind. And in case this assumption is broken, I'll have this check here, which will tell me, and then I can re-deoptimize. And deoptimize undoes optimization. It just sees, OK, we are not running with integers anymore. I'm going to swap out our turbofan frame for an interpreted frame. And now the function just executes normally, like as an interpreted bytecode function. So with slowest tier, but also the most correct tier. And yeah, basically, V8 just patches the stack frame while it's on the stack. Get used to this. V8 does a lot of technical shenanigans. But yeah, this is a good optimization trick, but there are some more variants of this. What happens if we do this? We have like a let constant with like a multiplier. We're multiplying with the multiplier. This is like a sort of common JavaScript pattern. If you know this multiplier should be constant, so that you know it can't change. But some people just do let bindings anyway, and V8 still wants to take advantage of this. So let's see what happens if we optimize this. OK, first of all, we're just going to see it. Yeah, it's normal function. Nothing to be seen there. We optimize. We still go through the dance. V8 seems to have inlined the constant. But noticeably, this time it doesn't have a check. Like, this is just a comment of like what the original source code line was. For V8's perspective, the function just multiplies by 2 no matter what you do. So, OK, yeah, it takes advantage of the optimization. It folded in the let constant. But why? What is it going to do if I'm just going to do this? OK, for this, we have to be a bit more careful and actually show like the interpreter internals. Like the interpreter handler for storing script values into like the context, so the multiplier value, will see that, hey, some piece of code depends on this being a constant. We're just writing to it. So we're just going to return the function to how it was before. And by the time we run the function, it's still just an interpreted frame again. We'd never observe this broken deoptimization guarantee. From like the perspective of a JavaScript programmer, we don't need to think about what optimization state V8 is in or like what assumption it has made. It just all works. And at this time, we have lazy deoptimization. Previously, we had eager deoptimization, where the optimization check came from the function itself. And now it happens lazily. It happens outside the function at the basically whoever is responsible for invalidating an assumption is responsible for notifying everyone of, hey, I just invalidated one of your optimizing assumptions. Meanwhile, eager de-optimization is more defensive. It runs in the function itself and rechecks every time. If you have a keen mind, you might have noticed an edge case here I have not addressed. Basically, what happens if we don't just assign it here, but do something like this? Basically, we have our compute function again, but this time we're taking a callback and getting a value from there. Optimizing, it will just give us the same result, just regular run through, all works fine, and it just runs. And still has made the assumption. Still no eager optimization check. Okay, so like what's different to this case from earlier? Well, what if I do this now? If we just go into it, we see we have call compute. Compute is optimized. Compute calls back to a callback. And now the callback makes the assignment. If like the V8 logic was just, hey, flag all code as being invalid now and make sure the next call goes to the unoptimized variant, how does it handle this? Because the optimized frame is still on the stack. If it just swaps it like the code pointer and doesn't do anything else, if it returns, we'll still run the optimized code. But V8 is smart, and V8 does one step as part of this. It walks the entire stack, looks for if the function it's de-optimizing is actually on the stack, and if so, it will patch the stack frame again. Just monkey patch the stack frame or the alive stack frame. Just okay. And yeah, it goes through, sees no other things. It's fine. Our callback returns now, and we don't return into like the optimized frame. We return into something V8 just wrote there. Basically, V8 does stack buffer overflows or stack rip control, but as a feature. Okay, and yeah, this built-in just does the usual thing. It does the de-optimizing, ensures that everything is like routed to the correct path. So yeah, in this case, it would actually like do the same thing as an eager de-optimization, so patch the stack frame to be a proper interpreted frame. And you have to keep in mind that some logic could have already run before the callback, so we don't want to just call the function again. We need to like jump into the middle of the function, which is something V8 can also do. As said, it takes a lot of technical wizardry to make JavaScript run fast, and V8 has technical wizardry. But yeah, and yeah, it just run, everything works normal now. Great. And we're back to our original function. But now we have a bit of a turning point. We can just like continue looking at source code, but then we're not really security researchers, we're just reading V8 and understanding it. At this point, one of my spidey sensors has been going off a bit. Like something might be wrong here, something might be subtly broken. No clue why, but that usually means I should dig into everything, not make any assumptions about what's correct, not assume that the Google people know what they're doing, because if you have that assumption, we can't just assume V8 has no bugs. Okay, so let's dig into this some more. And yeah, we have like this code here. Okay, we're in the optimizer.c. Okay, where does this lazy de-optimization boolean lead? It's defined here. It's read from here, from the optimizer, specifically from the de-optimizer constructor, which I assume from the class name is responsible for actually doing the optimizing. And doing some more tracing, we will eventually end up here at the optimized marked code. Not sure if you can read the line above, the comment, but it basically says, replace PC on the stack for codes marked for the optimization. Exactly what we've been talking about. Okay, so how does it do this? Okay, we have this activations finder helper, which just visits the thread stack and assumingly does the replacing. If we go in here, we will see that, yeah, it does this. It has another stack frame iterator, just like our function we started at. It will just see if any function is optimized. If it is, it will see if the function is marked for the optimization. If yes, it will find the trampoline PC it has to overwrite, because the function actually has a bunch of trampolines built into its source code, and I simplified, and it doesn't like jump directly into the built-in, it jumps into a trampoline to the built-in. Technical wizardry, we don't have the time. But yeah, once it finds a trampoline, it goes here, it sees, okay, new PC, it writes it into the patch. It patches the stack frame. There's some bunch of point authentication code, but looks fine. OK. So has anyone noticed the bug yet? It's a bit of a Chekhov's gun situation. I set things up intentionally. 5, 4, 3, 2, 1. Remember the stack switching thing? The first thing the unwind handler did, where it had handling for, OK, we encountered a stack switch, we need to follow a stack switch. That's not here. The entire function is really short, but they just don't have this handling here. So this activations finder won't follow stack switches. So what happens if we do this? Like, this is our original code, which worked fine. What if we just tweak this slightly? And instead of mutating our variable directly, we will first go through like the JSPI layer. We just, instead of like mutating the multiplier directly, we go through run. Run is a WebAssembly promising thing, which basically wraps a WASM function to make it run on a separate stack. WASM, I'm not showing the pseudo WASM code here. Basically, run just calls or callback. Call just mutate, does the actual mutation. So if we trace through this, we'll first have to do some setup, where V8 just evaluates everything, sets up WASM and everything. We run compute. Compute is still optimized. Compute calls a callback. We go into the callback. We go into run. We switch to a different stack, and we're running out of vertical screen space. Excuse the weird error routing. This was the best I could do. We have the WASM function. WASM just calls back to our mutate. Mutate has the usual script handler, which then sees, OK, something is optimized. We need to de-optimize. So it does the same stack framework. It just goes. Oh, the stack is over, I'm done. You missed something, V8. So what happens if we return now? We just go back down the stack frame, go down. We're back into our JavaScript land. We return from the callback. And we are in the optimized turboframe code. And V8 is just going to multiply x by 2, even though we just set it to 3. Congratulations, we found a V8 bug. But like, OK, we can make a function output the wrong result. OK, what is this going to do for us now? Well, lazy de-optimization is not just used for inlighting integer constants. It can also do some, let's just say, more important work. Like in this case, we have an array of doubles. So V8 sees, OK, this is an array of just doubles. I'm going to optimize it as just being an array of doubles and not of any arbitrary JavaScript object. Compute makes the same assumption. OK, it's just an array of doubles. I can just directly write a double into like the memory slot for this array. And our mutate suddenly stores an object in there. OK. What happens now basically means that we have the same thing going on. We mutate our array. V8 sees, OK, this array of just doubles now has an object in it. I need to make it more general. And basically transitions the kind of array from like one that only has doubles to one that can hold anything. This would usually trigger like a de-optimization, because some code might assume that the array only holds doubles and not do the check which kind of array this is. And in this case, we have just bypassed this logic. So with this new setup, once we return from a callback, we have just written a double into a memory slot that's intended to hold objects. And we have a type confusion primitive. And yeah, if you use this type confusion primitive, you can take control of the V8 heap. From there, you can build more stable primitives. From there, you can target the V8 sandbox. Yes, there's a sandbox in V8 itself. This is separate from the Chromium sandbox. Then you can find another bug there. This is early 2024, so finding V8 sandbox bypassers wasn't easy. These days, it's a giant pain in the ass that Google gives you 2.5K for. Usually, it was 20K. We'll see how that works out for them. But yeah, from there, you can get RCE in the renderer process. And congratulations, you have achieved nothing. Because the Chromium sandbox still prevents you from doing anything. But you have still successfully broken through most layers. And if this was Cloudflare Workers, you now have control over the host process, which runs your tenant, but a bunch of other tenants. And it's sensitive backend logic. And you can probably just, I don't know, sniff passwords from there. Don't get me started on like V8 isolates, like we use V8 as a security boundary. It's like, it's a different topic, so I'm not gonna go into it, but like, please really could like take care when using this for your own applications. Be aware that literally the next in the same process, some malicious JavaScript could be running that's trying to exploit you. Okay, now it's time for a demo. Where the heck is my mouse cursor? Okay, there it is. Is this font size large enough, or? Okay, yeah. Yeah, I have my original proof of concept from 2024. And it basically just does what we said. It has this callback. It has a simple WASM module that just calls back to JavaScript immediately. Then we create an array of just doubles. This fork map thing is some V8 technical wizardry. Then we have our function, which is compute. We basically store a double into what used to be an array, introduction array of doubles. We have inlined the callback, but this is just a callback from earlier. It just goes and calls a callback. Then we have some more black magic to actually optimize the method, because spoilers, I took some artistic liberties in the examples, and actually getting turbofan to run and not optimize things too much and not just like inline the function into your call site is a bit tricky. But yeah, this basically just does the same optimization loop. Then we change our callback from something that does nothing to like one that mutates the array. And then we just log what should be an object pointer. And we basically have, so basically it's exactly the same code flow that we had earlier. Now I just need to copy this experimental flag, because actually, like this is a bit spoiler free, like in the version of V8 that was targeting, technically JSPI was still an experimental feature, but it actually wasn't, because the Google ran experiments, so if you just enrolled your domain in the experiment, you still had access. So basically experimental, but still exposed to everyone. Yeah, so they understood if I told them to, hey, this is not experimental, still give me my money. But yeah, we can now just run a V8 build that has this unpatched, like, and just D8. We pass in our flag, we pass in the path for proof of concept, and boom. We have successfully interpreted a float as a pointer, and V8 is not happy about it. Yeah, I guess that concludes the demo, but now my terminal is locked up, so I guess I'll just need to do. Yeah. I think we're pretty good on time, so this concludes the technical part. And now for the meta part. Not sure if you're here for the technical part or the meta part. Now comes the meta part. Basically, V8, as you might have seen, is a really huge, really complicated code base. But it's also a really, really high stakes code base. So when you're looking at something, you have to basically assume that, first of all, a human reviewer with like really high knowledge has thoroughly investigated every aspect of the function, like of every single change that landed. And they will be thorough. This keeps going forever. I think V8 reviewers will as well if it's warranted. Well, yeah, they just will inspect every aspect of every code path. You can't just assume that some reviewer missed something easy somewhere. On the other hand, V8 is also extremely heavily fuzzed. So, like, making the assumption that some code path is dead code is also careful, like a bit of a wonky one, because chances are like that the Google fuzzer has already hit every code path imaginable at least a few times. So yeah. And in these days, you will also have to contend with LLMs running on everything. No clue what these things are doing, but they are also running on every bit of code in the code base by now. No clue what they're doing. Black magic, back boxes, I don't know. Okay. So what can you actually do as an independent researcher? Like, you have this really huge code base. You have this valuable target. You want to secure it, either for like because it's your job, or because you have a moral instinct to do so, or you have both. It's really cool when these incentives are aligned. But as said, like, how are you gonna find something in this code base if like you running up against an entire billion-dollar company. Basically, we have to one-up these people at their own game. And that doesn't mean just looking at a function in isolation and just seeing if they made a mistake in some code path. That might work on like every other code base, but not on V8. The thing that makes V8 exploitable and like probably never 100% secure is that it's huge. It's really complicated and intricate. As said, like we've seen like just one function, and it's like a hodgepodge of all of these different optimizations and tricks and technical wizardry that's been accumulating for literally over a decade by now. And you see all of these are interlinked in some way. And no memory safe language is going to save you from this. Like no compiler will find every issue. V8 is a compiler. Your attack surface is a compiler. So you can't use compiler tricks to secure this. So what are you going to do if like everything imaginable is looking at this? Basically, intuition and being aware of what's going on, like other side of you. As said, the reason I originally found this because at some point my intuition was just screaming at me and telling me something feels broken. My brain probably had this hypothesis of, okay, we have this lazy optimization thing. Is it actually sound? Not just make the implicit assumption something is sound because this is what the comments tell you, this is what the function names tell you, this is what the class name tells you, I don't know. You actually take a step back and dig into it yourself. You keep tracing down every source line until its end, until you have a full mental picture that's complete. And you dig deeper than every other V8 researcher can, because you have no time budget. You don't need to get the review done. Sorry for suggesting you have infinite time. I know you have like a job, and Google won't be happy if you just spend 1 week on a review. So you have, as an intermediate researcher, you have this time. You can dig deep. You can use your skills to actually understand V8 at a comprehensive level, not just the simplified talk overview here, but actually like know what every line does and what the assumptions are. You can then use this to make hypotheses about how some interconnected web of these components might interact in a way that no one has thought about before. In this case, we have JSPI, which is perfectly fine on its own. We have the lazy diop machinery, which works fine, even though it's scuffed. The thing is, no one just thought about these two things interacting before. And a very similar thing will basically happen everywhere else. You will find other components. Like I have said, I have more bugs than this, and every bug can basically be boiled down to something like someone made an assumption somewhere that turned out to be broken by some completely unrelated piece of machinery anyway. Okay, one bug was something where they just missed something, but it was still like a very, very intricate edge case where some control flow graph could have a shape they didn't think about, and that broke some assumption somewhere. It's still, you're never looking for typos or mistake, you're looking for broken assumptions that are non-immediately obvious. If it's something that can be found by a fuzzer, it will probably have been found by now. If it's something that could have been found during a normal human review, it could have been found. So you want to be really, really aggressive about finding your own hypothesis of like assuming everything is broken until broken otherwise, but you still want to like eagerly trim out anything that you know will have been found. So like if you have an assumption that some hot path is broken somewhere, then you can just assume that's fine. But like some edge case interaction of a new feature with an existing machinery that requires a very particular setup to actually hit the bug, that might slip under the radar, and that's where you can strike. So yeah, you find these connections, and you find these broken assumptions, these broken interactions, and hopefully get a bug. And obviously, it's not as straightforward as just looking at this function, going through everything. I made it seem a lot more linear than it actually is here. Like, as said, this was an 8-hour layover. I had prior experience from some V8 CTF challenges. This was not even my first bug. My first bug was like a trivial sandbox bypass from the early days of the V8 sandbox. The thing is, like, you still want to dig deep. You want to build a better mental model than anyone else has of some of your particular niche. And you want to find these hidden edge cases that everyone else missed. And that's also why I don't believe that, yeah, LLMs will find a lot of existing bug classes. They're really good if you want to like have a tree-wide search for some pattern. But if LLMs, at least in my opinion, are not able to like come up with these patterns, like these, they aren't able to do this deep comprehensive understanding and coming up with hypothesis and everything. I don't think they're really capable of this. So I think LLMs can boost like a human professional, but I don't think it's just that V8 research is over now. I have exited the scene because, as said, it's not commercially viable, and I'm really young, I have other things in my life to be focusing on, and this was always just like a side gig for me while I did uni and stuff. So this is not me saying it's still worthwhile doing. As said, if you're in it for the money, it's probably a bad time. But if you're in it for some other reason, or like in cybersecurity in general, I still believe that we will be around in some form. If your job is just being a manual human LLM, you might have a bad time. But if you are actually deep in the weeds, I think you'll be safe. You need to leverage the tools, of course, not leave left behind. Like in my recent searches, I have started using LLMs for like trivial refactors. But yeah. And yeah, that's basically my message. V8 is really complex. It's really cool. It's worthwhile looking at, and I don't think LLM will take us off a job. And that's also why I believe that these like new reward amounts are sort of bullshit. They're sort of just Google shifting resources around and not wanting to pay anymore, but I still think it's fine. And with that, we think we're perfectly on time, actually. So I think, I'm not sure if we're doing the math correct, but I think we have 5 minutes for questions and stuff now.
Yes, exactly. Thank you, Matthias. Great talk. Let's just start with the floor. Any questions? Up here in front.
Oh, sorry.
So it's less of a technical challenge, but the slides were fucking amazing.
Thank you.
How did you make them?
Motion Canvas, if that name sounds something to you, basically it's some TypeScript-esque procedural animation tool I've used before. The original author has sort of vanished off the earth and abandoned it, but there's community-maintained forks. To be honest, these slides were started at the start of the week, so this was, to some extent, I have used LLMs to quickly code stuff up, but LLMs produce shit. I have not had any sleep since yesterday. I spent all night polishing this, so thank you for recognizing my work.
Yes, so that was a quite productive layover, I would say. I would not be that productive myself, but the lesson I take away from this is like assume nothing and check what code's missing.
Yeah,
and
basically my rest will be aware of like other attack surfaces, like what other people are doing, and try to like specialize on this kind of intensive thinking work that like no one else is doing or little other people are doing, that tools can't hit, that reviewers won't catch. Basically, fill in the gaps. Be aware of what your state of attack is. Don't just mindlessly scan the source code, and spend your time honing your intuition, because like your intuition, your intrinsic ability to recognize patterns that are really deeply hidden, of just like having a hunch that something is broken, and maybe nothing is broken, but maybe you'll be right in 1 out of 5 attempts. And in the past, if you were right once a year, you still had a really good salary from this. So it's worthwhile honing these skills. And in an age of LLMs where like everyone is going, oh no, we have automated this, we have automated that, humans will soon be obsolete, I think I just want to like push back against the narrative a bit as well.
So thank you, Matthias. Big round of applause. Great talk, great slides.